Okay, morning class. Right, so where's others? Like only like 13 people here. Where's are the 22 more people? Hmm. Hmm. Can the monitor take the attendance for today? So I give like 2 more minutes, okay? For your friends to join before I start the class. Okay, so today we continue, okay, from our previous lesson, right? So I think we stop until here, right? Is it correct? Did we stop until here last time? Can I get the response? Did we stop until here last time? Okay. Alright, so let's continue. Okay, so can a satellite orbit the Earth, right, without being driven by a rocket engine? Okay. So prediction of the Isaac Newton said that a satellite can orbit around the Earth without being driven by a rocket engine. So how does the rocket can do this? Okay, without using the rocket engines, it can orbit around the Earth. Okay, so actually, the rocket needs, right? The rocket needs to be launched, okay, at the certain speed. Okay, so let's say if you try to launch it at the lower speed, okay, it will go back to the Earth. Okay, we go back to the Earth. So when you launch it with a certain speed, okay, and the speed is you can use the speed, right, to make the to make the rocket orbit the Earth. Okay, so it means they need a certain speed. So that's why before it launch, okay, the rocket, it needs to calculate first, right, what is the velocity that the rocket need, so it can orbit the Earth, right? So the prediction of Isaac Newton said the rocket can be the satellite can orbit the Earth, okay, without using any rocket engine. Okay. So the object launched with a low linear speed will follow trajectory 1 and reach the Earth at Q. So the first one, the launch with the low linear speed. Okay, so you can see the rocket going back to the Earth. Okay, and then okay, so the object launched with a sufficiently high linear speed will follow trajectory 2 circulating the Earth. So the object will not return to the Earth. So mean it needs a certain speed so it can orbit the Earth. Okay. So this is the Newton's cannon. Okay. So at first, right, you can see when it launched. Okay. Okay, when it launched with 5,900. So you can see it going back to the Earth. Okay. And then after that, we increase the speed, okay, to 7,200. Okay, and 8,000. So when you try to launch, you can see the cannon, right? The cannon orbit the Earth like that. Okay, without going back to the Earth. Okay, you can see it circulate the Earth without going back to the Earth. So mean it need a certain speed, okay, to be launched. Okay, so the rocket need the satellite need to be launched at the certain speed. Okay, so it can orbit the Earth without going back to the Earth. Okay. So if an object launch with a low linear speed, it will follow trajectory and reach the Earth. So you can see the first one just now, it comes back to the Earth. But the second time, if you launch it with a sufficiently high linear speed, it will follow trajectory circulating the Earth. Okay, so mean it will circulate the Earth like that. Okay. So the prediction of Newton is now a reality with so many man-made satellites orbiting around the Earth without being driven by any thrust. So you can see there's a lot of satellites, right? A lot of satellites, okay, that can orbit the Earth now, okay, without being using any force, okay, that make the satellite to move around the Earth. Okay, so it can just orbit the Earth around just like that. Okay. Okay, the satellite always experience gravitational force acting towards the center of the Earth. So the gravitational force on satellite act as a centripetal force. Okay, so when the so let's say this is the Earth, okay, and this is the satellite, right? So means there is a gravitational force that acting between the Earth and the satellite. So this force also, the gravitational force also is known as the centripetal force. Okay, centripetal force. So means the gravitational force that attract between the Earth and the satellite, we know it as the centripetal force also. So it's same, right? Okay, then we compare, right? We compare the formula, okay, for the force and the formula for the centripetal force. So we can obtain the centripetal acceleration. So based on the Newton's second law, that is F is equals to ma, right? And we know the force of the centripetal force is mv square over r. Okay, so if we compare these two, okay, so you can see A is actually equals to v square over r. Okay, so this is the acceleration, the centripetal acceleration. This is the centripetal force. Okay, so by comparing it, we can say that A is actually V is equals V square over R. Okay, that is for the centripetal acceleration. Okay, so example, okay, so this is on your textbook, right, page 93. Okay, so a weather satellite orbiting the Earth at the height of h is 480 kilometer. So what is the centripetal acceleration of the satellite? So we use the formula A is v square over r. Okay, so it already give you the speed here, 7.62 times 10 power of 3. Okay, and you have to square it, right? And the radius is 6.37, okay, times 10 power of 6, okay? But that one is actually the radius of Earth from here to here only. But the satellite is actually is at the outer space, so mean you have to consider the H here. So the H here is actually 480 kilometer. Okay, and you already see the unit here is in meter and this one is in kilometer, so you have to change the 480 kilometer to meter. So 480 times 10 power of 3. because kilo, the prefix value for kilo is 10 power of 3. So I just change it, right? And then you just use your calculator. So we get the answer 8.48 ms negative 2. Okay, right. So any question you want to ask about centripetal force, centripetal acceleration? No. If any question, you can ask in the chat box. Alright, so let's move on to the next one. Okay, so how you want to determine the mass of the Earth and the mass of the Sun by using the Newton's universal law of gravitation and centripetal force. Okay, so just now I already explained, right? When there is this, they say this is the Earth, okay, and this is the satellite. So of course, you know there is a gravitational force between these two, right? Between the Earth and the satellite. So this gravitational force also is known as the centripetal force. Okay. So mean for this one, you can put that mv square over r is actually is equals to g m1 m2, right? Equals to r square. Okay. We can make it it's equal. Okay. So from that we will derive. Okay. We will derive the formula. Okay, to calculate the mass of the Earth and also the Sun. Okay, so the first one, M. The capital letter M is actually the mass of the Earth, and M is the mass of the Moon. Okay, and R is the radius of the Moon's orbit. Okay, means from the Earth to the Moon. And then T is the period of revolution. Means how much the time is need to make one full rotation. Okay, means from here, okay, and come back to here. So that is the period of revolution. Okay, and then V is the linear speed of the moon. And if you want to find the distance, okay, the distance that the moon travel, okay, to complete one complete circle, okay. So we use it as circle formula. So you already know the circle formula is 2 pi r, right? Because this one is a circle. So you want to find the circumference for the circle, use the formula 2 pi r. Okay, and if you want to find the linear speed, okay, so you already know V is actually equals to S over T, displacement divided by time. Okay, so for this one we use the distance, right? So the distance here means how long does the moon, okay, travel, okay, to complete one complete circle here. So this one complete circle by using the formula of circumference. Okay, so 2 pi r. Okay, and then the time here means how much does the time for the moon need to complete one revolution or one complete circle. Means from here going back and come back here. So that is the T, the period. So that's why you can derive V is actually equals to 2 pi r over T. Okay, so from this formula, S divided by T. Okay, and 2 pi r is the circumference for the one complete circle, and the time is the period for the moon, okay, to make one complete circle. Okay, so that's how we derive for the V, right? Okay, so this one I already explained, okay, at the learning outcome just now, right? So the Newton universal law is F is equals to G M M over R squared. Okay, and the centripetal force is mv square over r. Okay, and I already also explained that, okay, the gravitational force, right, between acting between these two objects. Let's say this is the Earth and this is the planet. Okay, so already know there is a gravitational force that acting between them. Okay, so that gravitational force is equals to the centripetal force. So I can just equate two equation here. Okay, gm of mm over r square is actually equals to f equals to mv square r. Okay, and then I can just cancel. Okay, m over r square is mv square r. So I can just cancel these two m. Okay, and you will get gm, okay, r square, okay, v square over r, right? Nope, sorry. Okay, so how does you get that formula rv square? So let's say if I just cross multiply it, okay, so gmr is r square v, right? So this one also I can cancel. So this one only will be left by sorry, this is v r square. Wait. For a moment, gmr is r square v square. Okay, so I can just cancel this one. So it will become gmr v square. Okay, so this one is okay. So just cancel this one r. Okay, wait. Okay, you can see I cancel this one. So this one only left by only one r here. So gm is equals to rv square. So that's how I get this one. Okay, and then the next one. Okay, so I substitute. Okay, just now I already teach you how you get 2 pi rt, right, by using the formula v is equals to s over t, and the s is actually the circumference of the circle, right? When the planet orbit around the earth, it will make like a circle like that. So if you want to find the circumference of the circle, okay, you use the 2 pi r. Okay, and the period I already told you is actually how much time that the planet need to make one complete circle. Okay, so should be the period is t. So that's why you get like this. Okay, so for this one, gm, okay, r, okay, v is 2 pi r over t, right? So when I substitute inside here, rv square, it should be like this, square, right? And then gm r, okay, so 2 square is 4, pi square r square over t square. Okay, and then if I expand the equation, so it should be 4 pi square r cube over t square. Okay, and then if you want to find the mass here, okay, the mass of the earth here, so m is equal to, okay, so this one is actually multiply, right? So when it goes there, it will become divide, right? So r square, actually r cube t square divide by g. Okay, so you already learn fraction. If divide, you need to change it to multiply, right? So 4 pi square r cube t square multiplied by 1 over g. Okay, so I continue here. 4 pi square r cube. Okay, and then t square. So this is the formula to find the mass of the earth. Okay, so we derive from the equation. So we assume that the gravitational force, right? The gravitational force acting between planet, right? Between two planets or sun to the earth or sun to the any planet. Okay. So we just assume that the gravitational force is actually equals to the centripetal force. So from that, we can derive the mass of the earth. Okay. Okay, starting from this equation. Okay, and then we use the equation to find the velocity. Okay. So then we substitute in here. Okay. So that is how we get the mass of the earth. Right. So any question you want to ask for the derivation? derivation of the mass of the Earth equation. Any question you want to ask? Clear? No question. Okay, so since no question, maybe we can try to answer the exercise. Okay, how to calculate the mass. So what is the formula? So this is the formula. Actually, this one is R cube, right? Because R square times R is actually R cube. Okay, so you can see. Okay, so state the data need to calculate the mass of the Earth. So pi is actually a constant value, right? And g is also the constant value. So it's already you don't need that data because that one is actually a constant, right? Okay, like the gravitational acceleration is 9.81. So that one is a constant. Okay, we already know the value. It's not changing. Okay, but so what we need is actually the radius and the period of the evaporation. Okay. Okay, so try to calculate this one by using the formula 4 pi r square over gt. If you want to ask me any question, just ask. Okay, you can open your mind or you can just put in the chat. There are 3 people is not here, right? So can the monitor tell me the name of the people that's not here? Maybe I can call in the group. Before this, do you have an online class before my class? 7:30, 8:30, do you have an online class? So all of you is join the class or same people also didn't join the class. Can the monitor text me the name of the people who's not here? Teacher, can you go back to the slide just now, please? Oh, okay, you already have the handout, right? The notes, right? So, you mean here? Here we come. 4.06 times 10 power of negative 10 power of 13, 5.97 times 10 power of 24. Okay, any other answer? other than Kenny and also Shonki, any other answer? Same as Shonki, teacher. Erin and Isaac doesn't enter the class. Before this, did they enter the class? Before my class, are they joining the class? Same as Shonki. Okay, never mind. Okay, so let's see how you want to calculate. Okay, so you got two answers here. Okay, actually the answer is 5.97 times 10 power of 24. Okay, so you can just use the pi here. Okay, so 4 pi square, right? So on 4, okay, so the value of pi is given here. So pi, okay, and then you have to multiply 3.83 exponent 8, okay, and then close the bracket, and then you put the cube here, okay, power of 3, okay, you got the answer, okay, and then you divide by, okay, 6.67 exponent negative 11, okay, and then this one you have to multiply, okay, and you put the bracket because you need to square the radius there, okay, 2.36 exponent 6, okay, close the bracket, x square, okay, and then close again, okay, so the answer is, wait, did I 6.67 exponent negative, oh sorry, 11 times 2.36 exponent 6 square, oh I forgot to put square root there, right, so again, sorry, 4 shift pi, right, square, okay, and then 3, which times 3.83, wait, I forgot to put it. 3.83 exponent 8 close shift x3 here, got the answer, divide 6.67 exponent negative, this one you should put bracket, 6.67 exponent negative 11 times, okay, open bracket again, 2.36 6 exponent 6 square, right, and then put a bracket again, yeah, 4.97 times 10 power of 24, okay, so that's the answer. Okay, all right, so let's move to the next question. So any problem? Can you find the answer? For this one, you already calculate 2.01 times 10 power of 30 is for this question, right? Okay, so let's try to calculate this one. Two point zero one times 10 power of 30. Okay, you have to change the 1 year to second. So means you have to know that 1 year is 365 days, right? Okay, so 365 days you have to change to hour. and then hour to minute, minute to second. Then after that you can use the formula. Because they only give you R, okay? If you want to calculate the mass, you need the radius and also the period of regulation, right? So you need to 2.01 times 10 power of the 3. So let's check whether it's correct or not. Yes. Okay. So this one you have to change to second. Okay, so means 1 year is to 365 days. So 365 multiplied by 24. Okay, 1 hour. 1 day is 24 hours and 1 hour is 60 minutes, right? So 1 minute is 60 seconds. Okay, then you just multiply all this. Okay, you will get 31,536,000. Okay, and then this is the period here, right? So anyone, you want me to show you how to calculate this one by using the calculator? You want me to show you? No? Right. Okay. Okay, so we move on to the next one. There is Kepler's law. Okay. Are you sure you understand for 3.1 about the gravitational force? Okay, about the how we want to calculate the gravitational acceleration. Okay, and how we want to calculate what is the centripetal force. Okay, so the force is actually acting right towards the center. Okay, so you have to know how to calculate the velocity. Okay, and then the acceleration, not the velocity, the acceleration A is equals to V squared over R. And then you have to know how to calculate the mass, okay, and how we derive the mass of the Earth formula, okay, from the two equations, right, that we equate, okay, both of it. That G, the force of the gravitational force of acceleration is equals to the centripetal force, right? So I hope you are clear about that one, okay. So let's see for 3.2, okay, the Kepler's law. So actually when you are form 3, right, when you're form 3, you're learning about the law of orbit. I think on chapter 10 or chapter 11, I forgot, right? So you did learn that actually the sun is as at the center, right, and the planet will orbit right around the sun, okay. So that is the Kepler's law. So the first one we explain what is the Kepler 1, Kepler 2 and Kepler 3. Means what is the law of Kepler's law 1 and Kepler's law 2 and Kepler's law 3. So Johannes Kepler, so a German astronomist, right, a mathematician and astrologer who formulated 3 laws that describe the movement of the planets around the sun. Okay, so Kepler first law. So what does the Kepler's first law state? So it states that all planets move in elliptical orbits, okay, with the sun at one focus. This one, like I just said just now, the sun is at the center of the center, and the planet will orbit around the sun. Okay, but the shape, okay, is actually in ellipse. Okay, so all planets move in elliptical orbit with the sun at one focus. So this is called, or as this is known also as the law of orbit. Okay, so this is the animation, okay, to shows that this is the sun. Okay, this is the sun and the planet is, okay, rotate around the sun in the ellipse form. Okay. Right, so the activity 1, okay. So we assume, okay, and then the first one we do how we want to know, right, that actually it's true that the planet, right, the planet will orbit the sun in ellipse. Okay, so we draw 2 axes, okay. So this is the major axis and this is the minor axis. Okay, and then we put 2 thumbtack here. Okay, so the F1 we assume this is the sun. Okay, and F2 is actually the planet. Okay, right. So I will show you the video. Okay, how actually we want to draw this. Okay, so they put two thumbtack here. They already draw the axis, the major and the minor axis. Okay, so at the left part is the sun. Okay, and the right part is actually the planet. Okay, and they tie the thread, right, to the pen. Okay, so starting from the major axis. Okay, so goes to the another part. Okay, okay, so you can see it's moved in the ellipse. Okay, so you can do this at home. Okay, you can take two thumbtack. Okay, and then you put it on the paper. Okay, and then after that you tie the thread. Okay, and between these two thumbtack and also at the pen. So then you can move the thumbtack. Okay, let's say from the left to the right. Okay, and then you go back. Okay, at the upper part from here to here. Okay, first one you go from here to here, and the second time you go from here to here. So you can see that actually it move in the shape is in the ellipse, right? Not a circular. Right? It's actually almost like a round shape, okay, but actually we call it as an ellipse, right? Okay, so name the shape of bits used by the planet in the solar system. Okay, so we call it ellipse. Okay, so describe how the distance between the Earth and the Sun changes when the Earth makes a complete orbit around the Sun. So you can see the distance is further at the major axis. Okay, so you can see the distance here is further at the major axis if you compare with the minor axis. Okay, so discuss how the shape of the Earth orbit will be if the major axis is almost as long as the minor axis. So it will make a shape, right, that almost round. Okay. So the planets in the solar system have elliptical shape orbits. Okay, it's not like a round shape, but it's almost a round. Okay, but it's not just a round shape, and we call it as a ellipse. Okay, so the sun always stays on the focus on the ellipse. Okay, so it will be like a center of it. Okay, and the major axis is longer than the minor axis. So you can see here the major axis here, right, is longer than the minor axis here. Okay. And as such, the shape of the elliptical orbit of the planet in the solar system is almost round. Okay, so the planet can be assumed to make a circular motion around the sun. So the radius of the orbit is the average value, okay, of the distance between the planet and the sun. So let's say this is the average value. Okay, the average value, the radius, this is the radius, right? Okay, so the radius of the orbit, okay, is the average value of the distance between the planet and the sun, right? So that's the first Kepler's law. So it states that actually the sun, actually the planet, okay, orbit, okay, the sun, okay, in ellipse shape, okay. So that is the first Kepler's law. Okay, now we go to the second one, Kepler's second law. Okay, so Kepler's second law. So a line that connects a planet to the sun sweep out equal area in equal time. So this is called as a law of areas. The first one we call it as a law of orbit, right? So this one we call it as the law of areas. So what does this mean? Okay, this means, all right, you can see the area here, okay, CFD. Okay, the area of CFD is actually equals to the area of the F dA. Okay, so area of CFD, okay, is actually equals to the area of BFA. So this area is actually equal. Okay, but the time must be same, right? But the time must be same. Okay, so if a planet takes the same amount of time to move from A to B, okay, so let's say this one take like 24 hours, okay, example. So this one also must take 24 hours. So if this happen, so it means that both have the same area. Okay, BFA is equals to CFD, right? So if a planet takes the same amount of time to move from A to B and from C to D, the area is AFB is same as the area of CFD. Okay. So the distance AB is longer than distance SD. Okay, you can see here the distance AB is longer than the distance CD. Okay, so the planet is moving at the higher linear speed from A to B than from C to D. So this one is actually, we can use the formula V is equals to S over T. So when the distance is higher, okay, so of course the velocity also will be higher. So you can see here the distance from A to B is longer than C to D. So means here the distance is higher. So means at this part the speed is also higher if we compare with CD. Okay. So you can see the animation. How does it move? Okay. So when you reach at this part, you can see it move faster, right? Okay. And then we move here, it becomes slower. Okay. So it comes slower, right? And when the radius is decreasing, you can see, yes, the speed is become higher, right? And then it becomes slower again. Okay. Right, that is the Kepler second law. So we already learned Kepler first law. We know that the planet move, okay, move in the ellipse shape, okay, the ellipse shape around the Earth, around the Sun. So we call it as a law of orbit. Okay, the shape of orbit is an ellipse, and the Kepler second law said the area, right, the area of the A, B, C, and the C and B AFD, I think I can remember that one. But the area is same. Okay, and the time the area is same. If the time, okay, if the time also same. So if the time same means the area also will be same. Okay, and I will show you how does the planet move. Okay, at the smaller radius part. Okay, the planet move faster, right? So when the radius become longer, okay, so the velocity become slower. Sorry, the speed become slower. Okay, now we move on to the Kepler's third law. Okay, the square of the orbital period of any planet, okay, is directly proportional to the cube of radius of its orbit. So this is called as the law of period. Okay, so the first one, law of orbit. Second one is a law of area, and this is law of period. Okay, so the square of the orbital period of any planet is directly proportional to the cube of the radius of its orbit. So this one we have to derive the formula. Okay, so this is the time need, right, for the planet, okay, to make one full rotation. Okay, so let's say for the Earth 1 year, right, so 365 days. Okay, for the Mercury, they only need like 0.2 years, so means 0.2 times 365. Okay, so you will get how much time that the Mercury needs to make a full rotation. Okay, how much time they need to make a full rotation around the sun. Okay, so this is the period. Okay, so a planet which orbit with the larger radius has a longer orbital period. So mean this one, the longest one is the Neptune, right? Within 164.8 years. So it needs 164.8 years to make a full rotation around the sun. Okay, so planets which are further from the sun take a longer time to complete one orbit around the sun. Okay, for example, the Earth take 1 year to make one complete orbit, while Saturn takes 29.5 years. Okay, to make the full circle. Okay, one full circle around the sun. Okay, so mathematically, T square, okay, is a direct proportional to R cube. Okay, so T is the orbital period of a planet. Means the time it needs to complete one complete circle when it orbit around the sun. Okay, so that is T. R is the radius of the orbit. So mathematically, T square is directly proportional to R cube. Okay, so this is the orbital period. Alright. So formulating the Kepler's third law. So the Newton's third law can be formulated using Newton's law of gravitational and concept of circular motion. So planet makes circular motion around the sun. Okay. So the centripetal force is equals to the gravitational force between the sun and the planet. So this one, mv square g mmr square. Okay. So we just equate this formula, right? So mv square over r is g mm over r square. Okay, so you can cross multiply it. So you will get mv square r square. Okay, g m r. Okay, so this one you can cancel the common factor here, and r here you can cancel one r. So this one there is no r. Okay, so that only left v square r over gm. Okay, and then you get v square gm over r. So this is v. Okay, so this is how it gets this formula. Okay, v square is gm over r. Okay, and then after that, we already know how you want to find the speed, right? Before this, before we enter the Kepler's law, right, we derive, right? V is equals to S over T, right? So S is actually the circumference of the circle here, right? Means the orbit here. So it's actually equals to 2 pi r, right? And the time is the period for the planet to make one full circle, right? One full rotation. So that is a T. Okay. So I just replace V here, right? With the 2 pi r. So 2 pi r, okay, 2 pi r over T square. Okay, I just substitute V square here with the 2 pi r over T. Okay, so I square it because this one is V square, right? So gm over r. And then after that, okay, I square it for pi square r square over t square. So I will get this one. Okay, and then I have to cross multiply it. Okay, I have to cross multiply it. I put here. Okay, so 5 pi square r square over. Okay, so this one I cross multiply already. So I will get times r here, right? Okay, this one is gm over gm t square. Okay, gm multiplied by t square. So gm t square. So this one is actually 4 pi square r cube. gm t square. Okay, and I want t square, right? So if I want t square, means this one I have to move it here. Okay, so it will become 4 pi square r cube over gm. Alright, so and then from that Pi is actually the constant, is a constant value. G is also the constant value, right? Means the value is same. 6.67 times 10 power of negative 11, right? M is actually the mass of the earth. It's always constant. That is 5.97 times 10 power of 24. Okay, so this one I can put it like, okay, this one from here. Okay, the one I put in the circle, this one is all the constant value. Okay, so I can put it, okay, I can just group, right? Group like this. Okay, so it will become only left by R cube T square like that. Okay, and this one I can replace it with K. Okay, all this is the constant value, so I put it as a K here. I replace it with a K here. Okay, this one you already know, pi is 3.142, right? G is 6.67 times 10 negative 11, M is 5.97. So all this I can group it and I can replace it by one constant value. Okay, so I put it as a K here. Okay, so now if we left, like T square is equals to KR cube here. Okay, while K is a constant. So this is how we get the Kepler's third law. Right? Are you clear about this one? This one is actually like a maths one. Okay. Can you understand how does it derive? Okay. So this is the Kepler's third law. T square is KR cube. Right? So what is the K? K is actually this one, the 5 pi square over GM. Because we already know that one is a constant value. So later we can just replace the value, right? And we can just calculate the value of K. Okay, so derive the relationship. So this one we already derived. Okay, so this one also. Right. So can you try to calculate this one, this question? This one they ask you to find the radius of the orbit of Mars. Okay. So how you want to find the? Did I miss anything? Yeah, this one. Sorry. Okay, sorry. All right. So for here you got like this, right? Okay. So this one I already tell you. So this is K, right? Okay. So if like I have a two planet here. Okay. So let's say the first one is the Earth and this one is the second one is the Mars. Okay. So the planet one, let's say the Earth here. Okay. T1. Okay. So 5. This is K. Actually KR cube, right? KR cube here, and this one is also KR cube. So that's why they got like this. Okay. T square is actually equals to KR cube, right? And then they equate this equation. Okay, so this one I already show. T1 square is equals to R1. Okay, yeah, divide by R1. Okay, and this one is 2. This one actually it changed from here. Wait, I teach it. T1 square is KR1 cube. Okay, and another one is T2 square is equals to, sorry, is equals to KR2 cube. Okay, so I take K is actually T1, okay, over R1 cube, and this one is K is T2 is R2 cube, right? So K is actually the same value, right? So we can equate this. Alright, and then after that, we can cross multiply, right? So if I cross multiply, it will become like this. Okay, T2 R1 3. Okay, this one is T1 R2 3. 3 is mean the cube, right? Okay, and then okay, after that I can move the T2 to T1, okay, and this one R2 to R1. So it will become like this: R1 cube is divide to R2 cube is equals to T1 T2. Okay, square. Sorry, they got the square here. Okay, square, 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 square. Okay, so this is the last formula. Okay, so means you need to remember this one and this formula. Alright, so from this one you can calculate the question here. Okay, so use the formula T1 T2 square square R1 R2 cube cube. So this is the formula. Okay, so try to calculate this one. 2.28 times 10 power of negative 11. 2.28 times 10 power of 11. Okay, so let's check whether it's correct or not. So that's the formula. Yes. Okay, so the answer is 2.28 times 10 power of 11. Okay, you just cross multiply it. And after that you square the R value. Okay, the next one. Same, T1 square, okay, divide by T2 square is equals to R1 cube over R2 cube. So the radius of the moon, the orbit of the moon is 3.83. The orbital period means the T for the moon to make one complete circle is 655.2. Okay, and the radius of the earth is 6.37 times 10 power of 6. Okay, so we have to find the T for this satellite. Remember, you have to add the height of the satellite to the radius of the earth, right? $1.53 hours. So mean it takes only 1.53 hours to rotate around the earth. 1.53. So let's check whether it's correct or not. Yes, 1.53. Okay, so that's the answer. Okay, any other people who didn't give answer? Did you know how to get the answer? Do you want me to teach you how to calculate for this question? Others who are just keep quiet. You mean? Are you okay? Junket, is there any question you want to ask? Marian, Rachel? Okay, for tomorrow, right? For tomorrow, I will make a quiz, right? Online quiz. So tomorrow is a tutorial, right? So no, on Thursday. On Thursday there'll be a tutorial. So I'll make an online quiz. So all of you have to join. Okay. I will take it as your PBD. The question will involve for chapter 1, chapter 2, and chapter 3. Okay, so please be prepared. Okay, on Thursday during 2 period 1 hour, I give you like maybe 30 or 40 questions. Okay, so from that I will use that as your PBD for chapter 2 and chapter 3. Okay, right. So we finished chapter. So after this we goes to the geostationary satellite and non-geostationary, right? Only that last part for chapter 3. Okay, then after that we move on to chapter 4. Okay, I already assign you, okay, assign you a quiz at Google Classroom for chapter 3. So I hope you can go and answer the question. Okay, and I will meet you on Thursday, okay, for your online test. Okay, so I will call it as a test. Okay, so online test for chapter 2 and chapter 3. Right, so please be prepared. Okay, so thank you class. Okay, and for those who just, because I see just now like 3:34, only 1% still didn't join. So I want you to tell me why you joined this. Okay, and for those people who absent, can you ask him or her to text me to give me the reason why he cannot attend the class? Okay, so thank you class. Right, so have a good day. Bye. Okay, welcome. Thank you. Bye-bye. Bye.